So I want to develop the shell balance. Oh, the length of the pipe is L. So the heat is conducted all the surface, okay? So the heat is conducting everywhere. So we have to think about surface heat conduction area. Heat conduction area. 2 pi r is the circumstance circle, cross section, and this is the area. This is area. Okay. And this is a product. Sorry. So the heat is transported through the surface of the pipe. So we need area, this one, 2 pi RL, and the heat flux. Heat flux is the heat flow per unit area. So the heat flux should be equal because divide by minus 2 pi L PR, it's a very similar operation for momentum balance. So this differential equation could be obtained based on the shell balance. The shell balance becomes much easier for energy transport because temperature is current. Whoa. So integration of this term we could use, we could derive this one. Now, based on the Fourier's law, Fourier's law. We can derive QR could be replaced with this one. C1 dash. But we defined the integration constant with K C1. So we can remove the K by defining the constant like this. You understand me? Don't worry, heat is much easier. So we don't forget we have two boundary conditions. So the inner surface is TS and the outer surface is T. So we can integrate this equation and we can explain. So we have two integration constants. So at R equal kappa R, the temperature is Ts. So the Ts equals C1 Ln kappa C2. And at R equals large R, T equals TA. It means that TA equals C1 Ln large R plus C. So these two equations can be solved to obtain the C1 and C2. just rewriting that equation. So we can subtract this equation, this equation. So C1 becomes and C2 becomes so finally we can get our equation of something like that. T0 でやってるか。T ですって言ってるか。ちょっと違うな。T0 か。TA で T0 か。ちょっと違うな。どうしよう。まあこんなもんですかね。Okay. So finally, we can get this temperature distribution equation. So notation of textbook and my writing is a little bit different, but you can translate by yourself. So the problem is that why we want to derive the temperature distribution, because we want to know the surface temperature. Or if we set the surface temperature and inner temperature like this, how much the heat flow for keeping the temperature distribution. That is both. Heat flow. The heat flow this is the heat conduction area. And heat flux on the surface of the pipe. Okay, this point. So the heat flux is very useful. If you multiply the heat conduction area, you can know the heat flow. So this is a simple equation: heat conduction area and heat flux. So we already know the heat flux. And not now. This is a Fourier's law. Okay. So, we can derive the dTdr using this equation and obtain this term. When we replace the small r with large L, we can delete the large L this point and this point. So finally, so this is the heat flow of the pipe. So, okay. Do you have any question? Okay. So next week, I'm going to explain the situation B and C that could be explained in the page 283 and so to 285. And I would like to explain the many things. Section 10.3, 10.3, 10.3. So next week, much mathematics than this week. So please, ready for the next lecture. If you have any question, If you don't have any question, I want to finish the lecture. Or after that, please come to my here. OK, 終わりましょう。はい、お疲れ様です。